For some function f of x, its derivative, f prime of x, is an equation that gives the instantaneous rate of change of this function at any single point. And that instantaneous rate of change can be represented by the slope of a line tangent to this function at that point. And from Newton's quotient, we know that the derivative, which gives us the slope of the tangent line at any point, is just equal to the limit of the secant slopes, which would just be the difference in the y values divided by the difference in the x values of those points, where the difference in these x values, which we call h, is approaching 0. And in this video, I want to show you the top 10 derivative rules that you can use to find the equation of a derivative of a function without having to use Newton's quotient. Must know rule number 1, the power rule of derivatives. For this rule, if you want to find the derivative with respect to x for a power function, x to the power of n, notice the base of the power is our variable x, and the exponent n can be any real number. We can find its derivative using the power rule, which says you can take the exponent and write it as the coefficient of the power. You keep the base of the power the same, so it remains an x. And then you take the exponent and reduce it by 1. So the new exponent becomes n minus 1. And now let me show you a few examples where we can apply this rule. Looking at the first example, I see that I'm finding the derivative of a power function. Based on the power rule of derivatives, I know I'm allowed to take the exponent 5 and write it as the coefficient of the power. I keep the base of the power as x, and then reduce the exponent by 1. And 5 minus 1 is 4. So my derivative of x to the 5 is 5x to the power of 4. Applying that same rule to example number 2, where we're differentiating this power function, x to the power of 3 over 4, I can take the exponent of 3 over 4 and write it as the coefficient of my power, keep the base of the power as x, and then reduce the exponent by 1. 3/4 minus 1, that's 3/4 minus 4/4, which is negative 1/4. And then a proper final answer shouldn't have a negative exponent, so I can take this power which has a negative exponent, and I can move it down into the denominator with that 4 to change the sign of the exponent. And then lastly, for example 3, I know in finding the derivative, I can take the exponent and write it as the coefficient, keep the base of the power as x, and then reduce the exponent by 1. Negative 3 minus 1 is negative 4. And then since this power has a negative exponent, I could write its reciprocal so that it has a positive exponent, making my final answer become negative 3 over x to the power of positive 4. Must know derivative rule number 2, the constant rule. This is perhaps the easiest of all derivative rules. If you're finding the derivative with respect to x of any constant, so we'll say the derivative of c, where c stands for any constant, the derivative of any constant is just 0. So for example, if I asked you to differentiate the constant 5, the derivative of 5 is just 0. And there's a couple ways to understand that. Remember, a derivative is the instantaneous rate of change of a function. Well, how does a constant value change? It doesn't. That's what this answer is representing. And then graphically speaking, if I were to graph this function, 5, what does y equals 5 look like? Y equals 5 would just be a horizontal line through 5 on the y-axis. And since a derivative is the instantaneous rate of change or slope of a function, well, what is the slope of this horizontal line anywhere? Well, if I were to pick any 2 points on this function and calculate the slope between those 2 points, remember slope is rise over run, and since there is no rise between those 2 points, I know my slope would just be 0. Must know derivative rule number 3, the constant multiple rule. For this rule, if you're finding the derivative of a constant times a function of x, what that's equal to, you can just take that constant factor and multiply that by the derivative of the function of x. So this would equal c multiplied by the derivative of the function of x. And let me give you 2 examples of how this works. Looking at our first example, I'm finding the derivative of this function. And that function is made up of a constant factor, 3, multiplied by a function of x, x to the power of 5. So what you're allowed to do using the constant multiple rule is you can take that constant factor of 3 and put it in front of the derivative calculation. And then you know how to find the derivative of x to the 5 just by using the power rule. The derivative of x to the power of 5 is just 5x to the 4. And then you could simplify these constant factors of 3 times 5, you could simplify that to 15. making the derivative 15x to the power of 4. And you'll probably notice a shortcut that works if we have power functions like this. You can just take the exponent and multiply it by the coefficient to give you 15, and then reduce this exponent by 1 to give you 4. Let's try using the constant multiple rule for example 2 as well. We're finding the derivative with respect to x of this function, which is 8 times x. It's a product of a constant and a function of x. So this constant factor 8 can be moved out front. And if it helps, this x has an invisible exponent of 1. So when calculating the derivative, I can leave that constant factor of 8 and multiply that by the derivative of x. Using the power rule, I take the exponent and write it as the coefficient, keep the base, and then reduce the exponent by 1, making the exponent 0. And x to the power of 0 means there are no factors of x, so we could just erase it, which means the overall derivative is equal to just 8 times 1, which is of course 8. Must know derivative rule number 4, the sum and difference rules of derivatives. For these rules, if you're finding the derivative of a sum or difference of two functions of x, so f of x plus or minus g of x, what you're allowed to do when finding the derivative of a sum or difference of functions is just set that equal to the sum of the derivatives of each of those functions separately. So it would equal to the derivative of f of x plus or minus the derivative of g of x. And now let me show you with an example how this works. In this example, I'm finding the derivative with respect to x of this polynomial function, which is made up of 3 different terms. To find its derivative, I'm allowed to just differentiate all 3 of these terms separately and then just add and subtract their derivatives. And now we can just differentiate all 3 of those terms. The derivative of 5x to the power of 6 using the power rule, I know I would multiply this 6 by this 5 to get 30, keep the base of the power as x, and then reduce the exponent by 1, making it 5, minus the derivative of 4x cubed, 3 times 4 is 12, keep the base of the power as x, and reduce the exponent by 1, making it 2. And then my last term, the derivative of any constant, is 0. But you wouldn't have to write plus 0, making the derivative of this polynomial function equal to 30x to the 5 minus 12x squared. Must know derivative rule number 5, the product rule. For this rule, if you're finding the derivative of a product of two functions of x, so if you have the derivative of f of x being multiplied by g of x, the product rule would say that the derivative of this product is equal to the derivative of the first function of x in the product, so f prime of x, multiplied by the second function of x, g of x, plus the derivative of the second function of x, g prime of x, multiplied by the first function of x, f of x. So if we think of f of x as the first function and g of x as the second function, product rule says when finding the derivative of the product of those functions, you do the derivative of the first times the second plus the derivative of the second times the first. And now let me show you with an example how we can apply this rule. In this example, we're asked to find the derivative with respect to x of a product of two functions of x. For that reason, we need the product rule of derivatives. The product rule of derivatives tells me that I would have to find the derivative of the first function of x, and the derivative of 3x minus 5 would just be equal to 3. That needs to be multiplied by the second function of x. That's the first part of the formula done. Now I have to add the derivative of the second function times the first. So the derivative of x squared plus 1 is 2x. And that needs to be multiplied by the first function of x in the product, which is 3x minus 5. And now this is the derivative of this product, but we could simplify it into standard form. So I could expand the 3 into that binomial and expand the 2x into that binomial. And then collecting my like terms, 3x squared plus 6x squared is 9x squared. I have my derivative of 9x squared minus 10x plus 3. Must know derivative rule number 6. The quotient rule. In this rule, if you want to find the derivative of a quotient of two functions of x, let's say we want the derivative of f of x divided by g of x, I'll refer to f of x as the top function and g of x as the bottom function. When differentiating that quotient, that's equal to the derivative of the top function multiplied by the bottom function minus the derivative of the bottom function multiplied by the top function. And that all needs to be divided by the bottom function, g of x, squared. So let me show you with an example how you can use this rule. In this example, notice that we're finding the derivative of a quotient of two functions of x. For that reason, you need to use the quotient rule. And the quotient rule states do the derivative of the top function, the derivative of 3x minus 4 is 3, and that gets multiplied by the entire bottom function, x squared plus 5, minus the derivative of the bottom function, the derivative of x squared plus 5 is 2x, and that gets multiplied by the top function, 3x minus 4. And then all of that needs to be divided by the bottom function squared. So it needs to be divided by x squared plus 5 squared. And then of course you need to be able to simplify your derivative equation. So the numerator needs to be expanded and simplified. I would distribute the 3 to both terms in that binomial, and distribute the negative 2x to both terms in that binomial. And then in the numerator, I have a couple like terms. I have 3x squared minus 6x squared, which I could collect together to make negative 3x squared. So I'll do that below. And this is the final simplified version of the derivative of this quotient. Must know derivative rule number 7, the chain rule. This rule will allow you to find the derivative of composite functions, meaning if you have a function of a function. So that could be f of g of x. F is our outer function, and g is our inner function. So we have a function of a function. When that happens, when you have a composite function, you can find its derivative by differentiating the outside function with respect to the inside function, meaning find the derivative of f, so f prime, but then leave the inside function exactly as it is. But then that has to be multiplied by the derivative of the inside function. So we would multiply this by g prime of x. And this chain rule can be applied to all different types of composite functions. Since we've mostly been working with power functions up till now, I'll show you how this rule gets applied to a power function. If you're finding the derivative of a power of a function, meaning you have a power function, but the base is a function of x, not just x. So let's say we have g of x to the power of n. We could differentiate that by following the power rule, which says you take the exponent, write it as the coefficient. You leave the base exactly as it is, and then reduce the exponent by 1. But because this is a composite function where the base of the power is a function of x, we have to follow chain rule, which says we then have to multiply by the derivative of the inside function. So we have to multiply this by the derivative of the base of the power. So it needs to be multiplied by g prime of x. And let me demonstrate this to you with an example. In this example, we're finding the derivative of a power of a function, right? The base of our power is a function of x. It's not just x. So we have to follow chain rule when using our power rule of derivatives. I would start by writing the exponent as the coefficient of my power. I would keep the base exactly as it is, and then reduce this exponent by 1, making it to the power of 3. And then because the base of the power is a function of x, we have a composite function, meaning we now need to multiply this by the derivative of that base of the power. And the derivative of 3x minus 5 is 3. And then these constant factors can be multiplied together, giving us 12 times 3x minus 5 to the power of 3. And I would just leave that derivative in its factored form. And you'll see as we move throughout this video that chain rule applies to all types of composite functions, not just a power of a function, but it's also going to apply when we have trig functions or log functions or exponential functions. So let's move on to those as well. Must know derivative rule number 8, exponential functions. For this rule, if you're finding the derivative of any exponential function, let's call it b to the x, where b is any real number greater than 0, and x is our variable, which is in the exponent, which is what makes this an exponential function. When differentiating this, you actually keep the exponential function exactly as it is, b to the x, then that has to be multiplied by the natural logarithm of the base of the power. And let's also look at what happens if we make the exponent a function of x, meaning we'll need to see how the chain rule applies. When differentiating b to the power of not just x, but some function of x, let's call it f of x, we start by following the normal rule where we keep the exponential function exactly as it is. We multiply by the natural logarithm of the base of the power. But then because this is a composite function where we have a function of x in the exponent, I would then have to multiply by the derivative of that exponent. So this would be multiplied by f prime of x. And now let's do a couple examples where we can test out these rules. All right, let's have a look at these examples. The first one, I just want to differentiate this exponential function 3 to the power of x. And I recognize it's an exponential function because our variable x is in the exponent. I know when differentiating that, we keep the exponential function exactly as it is, 3 to the power of x, then that has to be multiplied by the natural logarithm of the base of the power, which is 3. And that's it. That's the derivative of 3 to the power of x. And in the second example, let's look at this very special case where we're finding the derivative of e to the power of x. Remember, e is Euler's number. It's that irrational number, 2.718, and so on. If I apply my derivative rule for exponential functions, I know I would keep the exponential function e to the x, and then multiply that by the natural logarithm of the base of the power. So I would have the natural logarithm of e. And the natural logarithm of e, that means what exponent goes on e to get e? Well, that's just 1. So this would be e to the x times 1, which is of course just equal to e to the power of x. Which is a very interesting answer, that the derivative of e to the power of x is actually equal to itself. The derivative of e to the x is e to the power of x. And for our final example, example 3, let's differentiate 3 multiplied by e to the power of 2x. Well, based on the constant multiple rule, I know I can just leave that constant factor of 3 and then multiply that by the derivative of e to the power of 2x. When differentiating e to the power of 2x, I would leave that exponential function, multiply by the natural logarithm of the base, and then because in the exponent we have a function of x, I need to apply the chain rule, which says then multiply by the derivative of that function of x. The derivative of 2x is 2. And then I could simplify this. The natural logarithm of e is 1, so I have 3 times 1 times 2, which is 6. And then I also have my exponential function e to the power of 2x. So there's my simplified derivative of my original function. Must know derivative rule number 9. Let's look at the rule for finding the derivative of the logarithmic function log base a of x. Notice for this function, our variable x is in the argument of the logarithm. And this a is going to be a constant value that's greater than 0 and not 1. The derivative of that logarithmic function is equal to 1 divided by the argument x multiplied by the natural logarithm of the base of the logarithm. So multiplied by the natural logarithm of a. And then also, if we make the argument not just x, but a function of x, we'll need to use chain rule. So for differentiating log base a of f of x, this would be equal to 1 divided by the argument, which is f of x, times the natural logarithm of the base, which is a, but then that has to be multiplied by the derivative of the innermost function, f of x. So this needs to be multiplied by f prime of x. And this f prime of x can multiply into the numerator with 1. And now let's try a couple examples where we test out these rules. Let's start by looking at the first example right here, where we're finding the derivative of log base 3 of x. Following my derivative rule, I know this would equal 1 divided by the argument, which is just x, times the natural logarithm of the base of the log, which is 3. And now in example 2, let's differentiate the natural logarithm of x. Following the same rule, this would be equal to 1 divided by the argument of the logarithm, x, multiplied by the natural logarithm of the base of this log. Well, this is the natural logarithm, so its base is e. So I'm multiplying by the natural logarithm of e. And the natural logarithm of e is just 1. So this answer would simplify to just 1 over x. And in this last example, we'll need to use chain rule because our logarithmic function, its argument, is a function of x. And I also notice this constant factor of 2, I can just leave that out front and multiply that by the derivative of this logarithmic function. The derivative of the natural log of x squared plus 1 would be 1 over the argument, x squared plus 1, multiplied by the natural logarithm of the base of this log. And since that's the natural logarithm, its base is e. And because the argument of the logarithm is a function of x, I need to use chain rule, which means multiply by the derivative of x squared plus 1, which is 2x. And now simplifying my derivative, I have 2 times 1 times 2x, that's 4x. And that's being divided by x squared plus 1 times the natural logarithm of e, which is just 1. So this is being divided by x squared plus 1. And there's the final answer. Must know derivative rule number 10, the derivatives of trig functions. Let's look at the rules for the derivative of sine x, the derivative of cos x, and the derivative of tan x. Starting with the derivative of sine x, the derivative of sine x is equal to cos x. And the derivative of cos x is equal to negative sine x. And the derivative of tan x is equal to secant squared of x. And then if any of these arguments were not just x, but instead a function of x, you would need to use chain rule. So let's say we were doing the derivative of sine, not just of x, but of a function of x, f of x. You would start by knowing that the derivative of sine is cosine. So this would equal cosine of, and you always leave the innermost function exactly as it is, so cosine of f of x. But then that has to be multiplied by the derivative of the innermost function. So this has to be multiplied by f prime of x. And now let's do a couple examples where we test out these rules. Starting with the first example, I want the derivative of 2 cos x minus 4 sine x. Well, when differentiating this, I can differentiate each of these terms separately. And when doing the derivative of 2 cos x, this constant factor of 2 gets multiplied by the derivative of cosine of x. So that would be 2 times negative sine x minus 4 times the derivative of sine x, which is cos x, leaving me with negative 2 sine x minus 4 cos x. And then in the second example, we're doing the derivative of 3 times sine of 4x. This constant factor of 3 will just stay out front, and we'll multiply that by the derivative of sine of 4x. Well, the derivative of sine is cosine, and then I always leave the argument exactly as it is, but because the argument is a function of x, I have to use chain rule, which tells me to multiply this whole term by the derivative of 4x, and the derivative of 4x is 4. And then to simplify this, I can multiply my constant factors of 3 and 4 together to give me 12. So my final answer is 12 cosine of 4x. And before I end this video, let me show you a bonus rule. Let me give you an example where you can see how implicit differentiation works. Let's say you're asked to find dy over dx for a function x squared plus y squared equals 1. Notice this y is not isolated. It's not written explicitly in terms of x. So instead of having to rearrange this algebraically and isolate for y, you can instead do implicit differentiation. And how that works, you would differentiate the first term with respect to x, plus I also have to differentiate this term with respect to x, but it's written in terms of y. So I'll differentiate it with respect to y to start with, but I really want the derivative of it with respect to x, so I'll have to multiply this by dy over dx. And you can probably see why we end up with the derivative of y squared with respect to x when we do this process. And then I'll differentiate the constant 1 with respect to x. Now let me find all these derivatives. The derivative of x squared with respect to x, well, using the power rule, that's just 2x, plus the derivative of y squared with respect to y, I can just use the power rule and it becomes 2y. But then don't forget there's a dy over dx beside that, and that's equal to the derivative of 1, which is 0. And now I just have to rearrange and isolate this equation for dy over dx. So I'll subtract the 2x to the other side, and then divide the 2y. And then simplifying this, I would find that the derivative of y with respect to x is equal to negative x over y. And there you go. Hopefully if you made it to the end of this video, you feel prepared to find the derivative of any functions you encounter. Let me know in the comments what you want a top 10 of next. Jensen Math!